In this video, we're going to learn about limits just graphically and numerically using a table. So, definition of a limit, you can all read it right here. I don't need to read it to you, but essentially what a limit is it's a y value. It's an approximate y value, so it's like an approximate height. It's not necessarily exact height. It is sometimes, but not all the time. Okay, so really the big thing here is the limit as x approaches some number a of a function is equal to this limit. So the limit exists if and only if we go from the left direction approaching a and going from the right direction approaching a, if they're the same values. So as you're approaching a limit on a graph, if the right and the left match, then that is your limit value. If they do not match, then the limit does not exist. And the same thing is true in a table. So we look at this graph down here. I'll kind of just draw it out for you a little bit because it looks like it's a little faded on here. So here's a graph of this function right here. So this function is given. We have a graph version of it, and then we also have a table version of it as well. So what I'm looking at here for the graph part is I find the limit as you approach 9. Well, here's 9. So what's the approximate height at 9 as you approach from the left and from the right? As we approach from both sides, they approach the same number. They approach a hole, and the hole is at 6. So the height is 6. That's how you know graphically what's going on. Now if we look at the table, so this says 9 from the left. So as we get closer to 9, here's the x value, here's the y value. So we have 8.9, pretty close to 9, but even closer to 9 is 8.99. Look at how the value jumps up a little bit. And then we go to 8.999, and you can kind of see this is getting closer and closer and closer to what number? 6. And then now on this side over here, 9.1, pretty close to 9. 9.01, even closer, and you can see as we get closer and closer and closer, look at these values, it's getting closer and closer to 6. Since the left and the right match, this answer is 6. So graphically 6, using a table, it is also 6. Now if you look at this example right here, go ahead and find the limit as x approaches 0 of this function h. Okay, so what we're going to do here is look at the left side. So this is going to be the limit as x approaches 0 from, I'll start with the right, it's a little bit easier. So I'm looking at 0. Okay, there's two things going on at 0. There's a one below and one above. Looking at the right value, so this is the right path. Okay, so what's the height on the right side as it's approaching? The height is 2. Well, what's the limit as we go to 0 from the left? Well, look at the left over here. It's kind of going up and down, up and down. It's really hard to tell, but it's definitely not 2. Okay, so this is actually going to be a does not exist on the left side. Again, because it's oscillating, and I'll get a little bit more to that when I get down here. So anyway, this does not exist from the left. So since these two do not match, automatically the limit as x approaches 0 of this function does not exist. You can just write dne. Anytime you get a dne value for a limit, you must show the right path and the left path. Again, anytime you get a dne for an answer, you must show the right path and the left path. Okay, so now let's go ahead and look at 2. So let's do the limit as x approaches 2 from the right. Okay, so looking on the graph here, the bottom one has the right path. So as we're approaching it from the right, we get 1. Now look at the left path. left path is up here, so we're getting closer and closer to the x value of 2, and that height is going to be 3. These are not the same, therefore the limit as x approaches 0 does not exist. Alright, and then last example, or last part of this example, is let's look at 4. Now, when you look at 4, you can tell that it does exist. So you don't need to show each side. So what is the height at 4 as you approach left, as we approach from right? They approach the same value, which is this hole. Remember, a limit can be a hole because a limit is an approximation. So this answer is just going to be a 2. Now let's talk about another way for a limit not to exist, and I talked about it up here. If you notice on this graph right here of this function, this is sine of pi over x. As you get closer and closer to 0, it's going to just keep going up and down, up and down, up and down. So it doesn't really have does not have a defined value, because you can even see in the table over here how it's just jumping as we get closer and closer. It goes from positive to negative to positive to negative, whether it's from the right side or from the left side. So since it keeps jumping over and over again, this would not exist. And again, that is because it is oscillating. And then last problem here. So we're looking at the limit as x approaches 0 of this function right here. If you were just given this function, it'd probably be easiest just to graph it. We are given the graph here. It's pretty nice. If you don't know how to graph it, just plot the point 0, 1, 2, 3, and then go to the negatives, -1, -2, -3. You would just plug those in. And obviously at 0, you can't have a number over 0, so that's why there's holes at 0. Okay, so here's the graph, and well, what do you see here? Are these going to match up? If I were to take my two fingers from the left and from the right, would they be the same height? Definitely not. So we know it does not exist, but let's go ahead and show it. So the limit, as x approaches 0 from the right, is going to be this one right here, which is 1. The bottom one there. As you approach 0 from the left, we get -1. They're different, therefore the limit x approaches 0 of x over absolute value of x does not exist. And that's it for this lesson.